Hi folks, welcome to lesson 12, energy dissipation and efficiency. I've mentioned this word in several other lessons and it's to do with not all energy transfers being useful. So if energy is dissipated to the surroundings, that's taken to mean that it is wasted, lost to the surroundings, usually heating up the thermal energy of the surroundings. So let's think about how that might affect the efficiency of various situations, various appliances, and let's start by looking at some images here. So what information can you get from these pictures? Let's pause the video and have a think about that. Okay then, so these have been taken with a thermal imaging camera. They detect infrared radiation, and the images are different colours here because the scale has been set up using a false colour scale, and different colours on these images mean that there's different amounts of radiation being given off. So here you are, this cute little dachshund here, one of Mrs. Staber's favourites no doubt, and his nose is giving off different amounts of infrared radiation from the rest of his body. So thermal imaging cameras can identify hotspots of wasted energy in machinery, and sometimes that can be due to a fault. So they can be used to identify faults in machinery. Okay, so here is a picture of a Newton's cradle. I'm sure you've seen one. If not, you can Google it on and have a look at what a Newton's cradle is. But if you lift one of these little balls up here, which is attached with very fine thread to the top here, and let it go, then it swings up the other side and so on. Okay, doesn't keep on going forever. They can go for a long time. But where does the energy end up? Where does it transfer to? If we had a thermal imaging camera on this, what would we see? Well, if we did have a thermal imaging camera, we might see a hot spot as these balls hit each other, transferring a little bit of energy between the two because of friction between up here where the cord meets the top. Okay, so this is where our energy, it gets transferred because of friction at various parts to the surroundings. Sound will radiate off it here as well, so eventually that's why our Newton's cradle slows down. So this is what we're going to be doing in this lesson. Pause the video and have a quick look at what your targets should be. Okay, so use your keyword definition sheets. Okay, this is a no slide, so you need to write this down. Okay, so whenever energy is transferred for something in a system, it's only some of it is usefully transferred. Nothing is 100% efficient. Okay, usefully transferred means it's transferred to where we want it in the way it's wanted, and if it's less usefully transferred, sometimes called wasted energy, then it hasn't gone to where we wanted it to, or it hasn't been transferred to the energy store we wanted it to be transferred to. So this is where the word dissipation comes in, because energy often is spread out, dissipated into the surroundings, and it usually ends up going to heat up to increase the thermal energy store of the surroundings. Okay, make sure you pause the video and get that down. This is also another no slide. This is Einstein. Okay, energy can be transferred usefully, stored, or dissipated, but it can never be created or destroyed. Okay, so there is always the same energy at the end of the process as there was at the beginning. So here's some examples. This is applying information. So chemical energy stores in fuel. This is for a jet plane, and these are transferred to a number of other stores by the engine. So the useful stores will be kinetic energy stores and gravitational potential energy stores as the vehicle climbs higher. But less energy stores will be thermal energy to the surroundings. Energy transferred by surrounding sound waves, also thermal energy transferred to parts of the components themselves. So what we need to do is identify where less usefully transferred energy ends up. So an energy transfer diagram can be quite a good way of showing that. So if we've got a chemical store of energy in our battery and we transfer that energy by an electric current to the lamp, then the lamp will transfer energy by radiation, and the thermal energy store of the surroundings increases. Have you seen here? I've put this is a useful exam phrase. I've already said that several times this lesson. That's really one to write down, folks. Okay, so this is there's two tables. I've got a foundation and a higher table, and we're looking at identifying energy pathways. Now remember, we did these in a lesson earlier on in this P1 energy topic, and then thinking about where does the wasted energy get transferred to. So we're thinking about how the energy is transferred and where it's transferred to. So you can pause the video, copy the table down, and then we'll go through the answers. Okay, so here we are then. So we're transferring the energy mechanically by the movement of the drum, and that should say by heating, but we will transfer some energy to the surroundings as well, and that's our wasted energy because that's not what we wanted from it. Right, I'll let you self-assess the rest. Let's see your green pens out. Here is a higher table. Okay, so you're thinking about where's the energy stored at the start, where's the energy transferred to, how's the energy wasted, and how could we reduce the wasted energy. So have a go at that one. I'll put the mark scheme next to attached to this lesson. Okay. Right, this would be a good point at which to work out what efficiency is and how we calculate it, and then we'll go through that afterwards. So have a watch of this video. So that means you need to pause this video, go and click on the link in the original PowerPoint, and then we'll come back to this afterwards. So the question for this video is, how do we calculate efficiency? Okay, now this is a no slide. I also have printed this off as a Word document, so it should be attached to this lesson if you're doing it from home, and if you're doing this remotely in school as a cover lesson, then the sheets should have been printed off for you, so you don't have to write all this down, just use the appropriate worksheet. Okay, so efficiency is a measure of how much useful energy is transferred out of an object from the total amount of energy that you transferred into it. So this is an inefficient lamp, so this could be an old-fashioned light bulb with a little wire in the end, in the middle of it, that gets hot as we transfer energy into it by an electric current. So it might well radiate out some light to the room. That's its purpose after all. But what we find is, if it's an inefficient lamp, a lot of the energy will have come down here, been transferred into heating up the room, as transferred as thermal energy, increasing the thermal energy store of the surroundings. Okay, now if we had 100 joules over here, and we think about what Einstein said, what he said was that energy wasn't created or destroyed, it was just transferred. If we've transferred 10 joules to lighting up the room, radiating out into the room, what number have we got here? Well, we must have 90 joules, mustn't we? Because 90 plus 10 is what we put in. We put in 100 in total. So think for a second, what would a more efficient energy transfer diagram look like? A more efficient one. We're transferring more of the energy to where we wanted it to go, so more energy into lighting rather than heating. So the arrows showing the light radiating into the room would be thicker, and the arrows showing the energy going into the thermal energy stores of the surroundings would be thinner. So write this bit down, please. This is what you need to know. Efficient devices transfer more energy to where we want it to go and transfer less to heating up the surroundings. Okay, so from the video, you should have got the efficiency equation. Now there's actually two of them, but effectively they're the same because one uses energy and one uses power. So if you know one, you'll know both of them. So to write it out, efficiency is the useful output energy transfer divided by the total input energy transfer. Okay, so in other words, useful output divided by total input. That means that you've got the larger number on the bottom always, and if you haven't, you've got the equation wrong, so that's worth checking. So it's always written the answer as a number between 0 and 1, and it's got no units unless you've multiplied your answer by 100, and 100 means percentage means out of 100. So if you multiply your answer by 100, then you will have a percent. But if you've left it as a number between 0 and 1, then you don't have any units, and that's a bit unusual in physics. Okay, so the other way of writing it is using power, but again, it's the same thing. Useful power output divided by total power input. Okay? All right, let's practice some. So I'll leave these questions here. 5,000 joules of energy are put into the motor, so that's the input energy. and the motor transfers 100 joules as useful kinetic energy. That means it's a very inefficient motor because it's wasted 4,900 joules effectively. But can you work out how efficient that is? Okay, remember, you're going to put your useful output divided by your total input. Your useful output divided by your total input. Right, I won't say any more. Have a go at those. Okay, I hope you paused the video. If you haven't had enough time, make sure you do pause it now. Okay, so here we go. So our 100 divided by our 5,000 equals 0.02. You can stop at that point. That is how efficient the answer is. I said it would be a number between 0 and 1. If you do multiply it by 100, then you must put down the percent. Okay, you don't have to do that second bit. All right then. Laptop converting 400 joules of energy into 240 joules of useful energy radiating out so that we can watch and hear it. What is its efficiency? 240 then, divided by 400, bigger number on the bottom, remember, equals 0.6. That's the efficiency. If you do convert it into percent, remember to put the percentage sign. Where does the rest go? Dissipated to the thermal energy store of the surroundings. That's what I told you. That's a useful exam sentence. This was the challenge one because it said a steam engine is 50% efficient. Actually, I've just realised it's not that much of a challenge, is it? Because 50% is half. However, let's do it properly. 50 divided by 100 will give us our 0.5, which we then substitute into the equation because we've got 20,000 joules of movement energy. How much was put in? So you're going to rearrange the equation to give you 40,000 joules. 20,000 divided by 0.5. Okay, so at this point you can pause the lesson and you can try some of the attached worksheets. Okay, so to finish, foundation question. Total input to a pumped storage power station is 600 megawatts. Useful power output is 540 megawatts. Now they're in the same units there, so you don't have to transfer those both to watts, although you could. And calculate the efficiency, so use the equation. Okay, there we go. So our 540, the output divided by our input to give us a small number, less than 1, folks. That's your check. If it's the other way around, you've done it wrong. Don't have to convert it into percentage. Strongly recommend you don't. Just write down 0.9. You'll still get the full marks. If you do convert it into percent, by timesing it by 100, make sure you put the percentage symbol. So how much power was wasted? Well, you've had 600 going in, and you had 540 coming out as useful energy. Then you've actually, in this case, wasted the difference between those two, which is 60 megawatts. Okay, here's a higher question. To give the main way that the motor is likely to waste energy. Okay, motors always involve movement. Think about that in terms of your friction. And then work out what the total power input to the motor was. When the total power input was 5 watts, the motor could not lift the 2.5 weight. What is the efficiency of the motor? Okay, so let's go through our answers when you've had time to calculate that. So have a go. Pause the video at this point. Alright, and there you go. Alright, and just as a plenary, once you've marked that, please, which of these two bulbs is an energy efficient one? Oops, I left the answers up. So if we have a look at it here, then we'll just discuss it. This one, you can see, is emitting more thermal energy than this one. So this one is wasting more energy because that's not what we want from our light bulb. Okay, again, taking the thermal imaging camera, which takes us back to the start of the lesson. Okay, well done.